Hi, everybody. It's nice to see. I basically think I recognize everybody. Good morning. Nice to see all of you. So I think maybe one or two people. For people who don't know who I am, I'm Anthony. This is the Arthur Compton lecture series, and this is the 7th out of 8. So we've really come a long ways. And I wanted to start off with kind of 3 non-lecture-based things. So a lot of people have been asking me for books and things that I recommend for both like a general overview and then some things that are more specific. And so the books that I recommend are, one is an extremely famous book, and this is the first edition picture of it, The First 3 Minutes by Steven Weinberg. And it gives an account of what we think happened in the first 3 minutes of the early universe. Which is a lot of what we're talking about. So if you remember that picture I put up where you see the evolution of the universe and where particle interactions are really important, this book is a beautiful rendition walking through it. And then this is Particle Physics, a very short introduction, and this goes into a bit more specifics in particular for particle physics, but still at an overview level. And then if you want to start going more and more detailed, these 2 books over here, At a Leading Edge, the Atlas and CMS LHC experiments. This is a book that when I started grad school, our advisors were like, read at least the first few chapters of this. And it really gives you a good introduction to the specific ideas we're talking about. And in this book over here, if you get through all 3 of these and you want something that's much more for an expert level, this one over here is something that my undergrad advisor had a set of books on his ledge and was like, this book, if you can understand all of this, you will understand everything that we're doing. So, this one is yeah. I can't even read this fully right now. So, yeah.
How old are these books?
How old are these books? So this one I think is 2010s-ish. This one is roughly the same time. I think all 3 of these are roughly the same time, and then this one I think dates back to even the 90s. And there's been updated since the 80s. Yeah. So this one, there's been multiple renditions of it. So Steven Weinberg, he was one of the Nobel Prize laureates, and so he released multiple updated versions of it. But the first one is really, really good.
So all of these are available.
Yeah.
Easily available.
Yeah.
Thank you very much.
Yeah. And then the second thing I wanted to mention was this week there's actually 2 big things that happened. So there's a bunch of, at the national labs, at the national lab near Stanford, SLAC, and at the national lab on Long Island called Brookhaven, there's a bunch of events happening right now to celebrate the 2 big events that happened recently, or 60 years ago and 50 years ago recently. So the first discovery of charge parity violation was 60 years ago, and this was the 1980 Nobel Prize. And they studied particles known as kaons at Brookhaven National Laboratory. So this is on the peninsula of Long Island. There's a national lab just like CERN or just like Fermilab, and they did pioneering studies there. And then the second one is that around 50 years ago, there was the discovery of the so-called J-psi particle, and this was the experimental evidence for the charm quark. So this put the quark model on strong footing, and what they saw was exactly that at this number around here, around 3 GeV, so 3 times the mass of the proton, this beautiful peak. And here, if you go and check out the CERN article, you'll read about something that was called the November Revolution, where on both sides of the country, completely independent of each other, 2 different experiments discovered the same thing, completely unknown to theory before. So they both discovered them, and then in some weird coincidence, the director named Sam Ting flew out to Stanford, talked to the director, and then it became known that both of them had the same discovery, and then they put out a joint press release, and in the roughly 2 months afterwards, particle physics exploded massively. So you can go and check out that too. And the third thing I wanted to show you was if you go to the CERN website right now, you can see an event display that actually I've shown you a few times, which is a discovery at my experiment. So Atlas observes top quarks in lead-lead collisions. And so what we're talking about is top quarks, the most massive types of particles being produced in 2 lead ions. And why people are really excited about it is when you collide 2 lead ions, you produce a state of matter that's like protons and neutrons melted down. And you can ask, when did this exist? And it existed in the early universe right before all of the nuclei that now exist was formed. And having this observation of top quarks gives us a new probe for this material. So we can use the top quarks interacting with the plasma that we produce to learn more about it, and then infer new details about the early universe. And so why I'm showing this is actually my research. So I'm really excited that this actually came out. And OK, so now putting a pause on that. So now today what we're going to do. So today I'm hoping what this will be is a type of lecture where you can sit back and you can think about just how much you've learned and how much you understand, and put a lot of pieces together. So I personally really enjoy towards the end of like a class when you have a lecture where you see something brand new and you see how all of the pieces from the different lectures kind of go into this new one, and you can really understand the frontiers of research. And so what we're going to do is we're going to first do a refresher of the past 6 lectures, very quick, and then we're going to look at a brand new result coming out of the LHC. It's actually one that was posted, I think, a month and a half ago, so really brand new. And I'm going to show you how basically everything that you've heard over the past 6 lectures are the key ingredients to this whole new result, and by extension, all of the new results from the LHC. So if you recall from lecture 1, the essence of lecture 1 was this plot here, which I said was my second favorite plot, and you've seen many times now, where along this axis, you shoot in 2 protons, and you look at interesting types of physics that can come out, like, for example, production of a Higgs boson, and then you ask, what is the probability to see that? And so what I hope you took away from that is that what we're dealing with is a probabilistic universe, not something deterministic. It's not like we can shoot in 2 protons and exactly get out the same thing each time, because there's a probability spectrum. And so what we needed to do was we needed to discuss an experiment or a tool that can force billions and billions of particles to collide. And that tool is what you see in the background and what we've been talking about, the LHC. And then in lecture 2, we talked about the big picture of physics questions. And so this was a lecture, if it was like me, your brain was very confused for a lot of it, and you went, wow, these are 7 big questions that we're talking about, ranging from all different time periods of the universe, different types of physics, to Higgs boson physics, nuclei physics, cosmic physics, dark matter, dark energy. We posed 7 different questions, and they really centered around the standard model. They centered around things like the matter-antimatter asymmetry and how we could find new physics that could help solve these problems. And then in lecture 3, we transitioned from theory to experiment, and we started to think about how we could use these big machines to actually answer a basic question in science. And the question that we thought about was, how do particles get mass? And so we talked about how there was this collider at Fermilab, and there was a collider at CERN in the 90s and 2000s that started to hint at that there might be a Higgs boson. And then we turned on the LHC, and after a few months of running, we actually made the discovery, which is now the centerpiece of the standard model. And so this helped transition our brain from the theory side, billions of collisions, to actually using the experiment to make a discovery. And in doing that, analyzing a lot of data. And so we mentioned different forms of AI. So narrow AI, doing specific tasks, general AI, which is supposed to accomplish a bunch of different tasks, and then super intelligent AI that is better than humans. And so then we took that, and in lecture 4, we talked about a first version of narrow AI, which was using AI to infer particle properties. So we talked about how when 2 protons collide, you get all these detector signatures. And what we're interested in is the physics that's happening at the femtometer scale. So extremely, extremely small. And we liken that to putting a top quark here on Earth, and then the meter scale being 1,000 times the distance from the Earth to the sun. So we're trying to use measurements from the detector at meter scales to infer things at the microscopic scale. And we're doing that nowadays using AI. And then in lecture 5, we talked about actually how we save the data and how we do so many billions of collisions that we produce so much data that we can't actually save it all. And so we design algorithms to save it, and we save less than 0.01% of the data. And so the pathway that we talked about is from the real experiment through something like 3,000 kilometers of cables into custom electronics inside of here, where we make decisions of what data to save, and then that data gets saved to warehouses of computers where you have something like 400,000, 500,000 cores. Yeah?
So the protons, when they
So the question was, we said that when two protons collide, we can produce one Higgs, and then I think your question was to produce multiple Higgs, how much do we need oh.
It would require just two protons
Yeah.
to produce Higgs,
Yeah.
or is it many protons are needed to produce one Higgs?
It's, you only need two to collide to produce a Higgs, but the probability of that happening is so rare that you need to do it billions of times before you even get one.
Which means that two protons,
Yeah.
that only the mass, 2 times the mass of a proton,
Mm-hmm.
can produce a mass that is 125 times.
Yeah, you can get a narrow resonance from them. Yeah. This is the energy and mass conservation. Yeah. Yeah, we can talk about it more later. Yeah. Yeah.
How is like the data like saved before it gets to the actual computers?
Right. So the question was, how is the data saved before it gets to actual computers? And if I,
How do you get the data to decide like what to compose it?
right,
If you don't have space for all.
right. And so if I remember right, I don't think you were at this lecture. Is that, do I remember that right? I can give a quick,
I don't
yeah.
like last.
Yeah. And so the question was, how do we actually get the data? So I can give a quick, so what's happening here is you're shooting in two protons, they collide, then a bunch of particles come out, they hit detectors that are sitting around. So like, for example, this is one detector cell. And actually the picture of the detectors, they look like this. In those detectors, there's electrical channels, that each electrical channel will generate some amount of bits. And we're talking about billions of electrical channels. And then on the detector themselves, there's basically computers, different types of computers, but computers that make decisions and then pipe the data over fiber optic cables to a warehouse nearby, so underground nearby. And then that data then gets sent also through cables to a nearby computer farm.
I see. So the
Yeah.
cables are just so large that only enough
Yeah.
a little bit of data gets, or there are so many cables that data like only gets to a little bit at a time.
Yeah. Yeah. Roughly, yeah. Yeah. Yeah.
So each experiment, in a sense, has its own set of triggers? Are there multiple experiments sometimes running at the same time?
Yeah. So the question was, each experiment has their own set of triggers, or there's multiple experiments running. So at the LHC, we have 4 major experiments. So there's the one that we've been talking about a lot that I'm on called Atlas. Then there's CMS, LHCb, and Elise. And in those experiments, you have thousands of different triggers running simultaneously. Yeah. So there's multiple layers of yes. Yeah. Okay. And then last lecture, we talked about simulation. And so a lot of the plots that we've been showing, we showed data on it, and we also showed simulation. And we said that the data is consistent with the simulation. And so what we did last time was talk about the basic ingredients that go into that. And so we talked about Feynman diagrams and how those were actually representations of math being done. We talked about computing that math automatically using algebraic manipulation. So things like Schoonship that was invented in the 70s to do it automatically, now Mathematica and other things like that. And then we talked about approximating the very high dimensional integrals that you need using Monte Carlo methods. And then we saw that after doing all of that, we could get one box that then we run it and we get extremely, extremely vibrant event displays where this is just entirely simulation. There's no data inside of this. It's a pure simulation of 200 protons colliding simultaneously, producing some interesting physics and interacting with the detector. And so today, now what I'm wanting to do is see it all in action. So what I did is I went to our public site where you have the collaboration posts news stories, which are basically summaries of really modern results. And I took one of them, and I took the one that actually I worked a lot on myself. And so there's an article, and then this is the actual paper. And now what I want to do is walk through basically from the start to the finish. I won't put screenshots of the paper like that, but start to finish roughly and show how everything that you've learned is exactly the ingredients to the entire thing. And at the end, you'll see a result that looks very familiar, like what you saw lectures ago about the Higgs. And so that's going to be what we do. We're going to walk through this, and then at the end, you'll hopefully understand basically all of it, and then we'll be able to talk about the future directions that you could imagine doing next with it. So I'll pause a second and ask for questions, and I will also say this is a lecture because it's going to be getting your brain to connect a lot of dots. Any moment there's a question, just, I don't think people are shy, but any moment there's a question, just raise your hand and jump in. Yeah. Okay. So I think the best way to start is just, oh yeah. Yeah. No, for it.
This is a global approach to this problem. Graduates, postgraduates, all involved. I'm curious about the writing of the paper itself as we get together to plan to write what
Yeah.
you're about to show us. Perhaps maybe I should withdraw and let you finish and then come back to that.
Yeah, I can. So the question was, when we actually write the paper, what does writing it look like? So I tell you because we just wrote one. Basically what happens is you get some format, general format, then the grad students and the young scientists put a draft together, and then for us, we then circulate it to the 3,000 physicists in the collaboration. People give comments on it, just on physics comments to start. And then we do iterations like that. And then the final one, some people who are much better at English than me come and say, you need a comma there, you need an apostrophe there. And we go through iterations like that until we end up at something. And then we submit it to a journal, and then you do processes like that. Yeah.
What's the conclusion?
Conclusion?
What did you find out?
From this one, we set limits on a new type of particle production. We didn't find new physics. But we were able to probe, basically, never before explored phase space. Which,
You didn't find this supercell.
no. Or else the first lecture I would have told you. Yeah. So the question was, what is the result of this? And the essence of the question is, we've already heard many times that we haven't yet found new sign of particles, and so are you going to now tell me that we've actually found something? We haven't yet found something, but what I'm hoping to do is walk you through something that really uses a lot of brand new techniques, and as the LHC starts taking more and more and more data, we're going to have a factor 20 basically increase. Yeah, the limits will change, and all these techniques, you'll then see an explosion of papers that come out, and you'll be able to understand basically all the new results. Okay. So the thing I first want to do, which is the thing that I usually do, is I start off and I look at this and I say, what is this title even saying? And so here I see a search for something R parity violating supersymmetry in final states containing many jets in proton-proton collisions at 13 TeV with the Atlas detector. And so I translate that, and what's the motivation? We're trying to find new particles. Basic. So this whole line here means we're trying to find new particles. And then the next bit is the signature we're looking for. So like in that lecture where we talked about inferring particle properties, where we talked about how the top quark could lead to a W boson and a B quark, and that leaves a jet of particles in the detector. Here what we're looking for is a similar type of jet, but actually we're looking for many of them. So many sprays of particles. And I'll show you an event display where you can see things like that. And we're looking inside the Atlas detector. And then the data, how we're actually producing this, is high-energy proton-proton collisions. And so then you can ask, okay, what's the motivation for doing this? And what we're trying to target here is two major puzzles in physics that you heard about in the second lecture. And so we're trying to target the hierarchy problem, which is the question of why is there a large gap between the gravitational scale and the weak scale. So we heard that the weak force is much stronger, or in other words, the scale is much lower. So here, this is a picture from lecture 2 where we put the weak scale, which is basically everything in the standard model, down here. And then we said 19 orders of magnitude up here is where the gravitational scale sits. And so that's one of the puzzles we're trying to solve. And then the second one is the matter-antimatter asymmetry. And so this is the statement of if we look out in the universe, we see an excess, not an excess, well, roughly an excess. We see more baryons or matter than antimatter. And the general prescription that we talked about in lecture 2 was that these problems and the 5 other ones that we talked about, new physics could come along and provide resolutions for them. And so the new physics that we're interested in, again, how the paper goes, is that what we're doing is looking for a new particle. And so those new particles are these 2 here. And the logic is that these new particles could help solve the hierarchy problem, or this gap in scales. And so what we mean is that this particle would be more massive than the Higgs boson. So if the Higgs boson is at this scale here, this new particle would be up here and serve as a bridge between the weak scale and the gravitational scales. And so in doing that, you would resolve these type of fine-tuning problems. And then the second thing is that we look for these particles decaying in particular ways. So we have a new particle here, and then it decays, in this case, to 3 quarks each. So quarks just like the standard model particles. But the interesting thing is this process here actually violates something called baryon number, which can produce a matter and an antimatter asymmetry. So to say it one more time, we have 2 problems that we're targeting. So we have this large data set, and we're asking what problems can we try to resolve with it. And the problems we're interested in are the gap between the weak scale and the gravitational scale and the observation of more matter than antimatter. And so we postulate new particles, we postulate new couplings, and then we actually go and look for it. And so when you go and look for it, you have so much data. And at this point, with so much data, it's really like looking for a needle in a haystack. You have 2 really important features of this. One is that these type of particle prediction is extremely rare. Extremely, extremely rare. And I'll show you on the next slide just how rare we're talking. And the second thing is that the signature that it leaves in the detector is almost identical to signatures that known physics can leave also. So when you do a bunch of proton-proton collisions, they looked almost exactly like what you would produce normally. And so when we say rare, just how rare are we talking? And so this is that plot that you've seen before, and this is a plot that you've seen before in a different fashion. So this is along the x-axis, this new particle mass. So it's this new guy here. And then along the y-axis, it's the probability to make it. And this purple line is what we're following. And so if I map this purple line onto the plot that you're familiar with, it's this whole region down here. And what we talked about in lecture 1 is that to get a single particle right here, you need around 100 billion collisions. So to say that again, to get the easiest way that this new particle could be produced at the lightest mass, to get one of them, you need 100 billion collisions. But what we're interested in is probing from here all the way down to here, and that's a change of 5 orders of magnitude. So instead of needing 100 billion, you could need 10 million billion. Yeah, so really a different scale than what we talked about even in the past. Yeah, and then I'll come.
So I understand the motivation, but is the motivation when it came up, then go back and look at experiments that already happened, or did that motivate a specific new experiment and then collect the data?
Right, so if I understood the question, it was we have these motivations, and then what is kind of the chronological ordering? Do you then go look at old experiments, or then do you go take new data? And so for this one, as this motivation was being formulated, we looked at all of the old experiments, so before the LHC, and then we designed new triggers to take data in with the current experiment. And you'll see an example of what I mean by that. Yeah.
You're looking for particles that are really heavy,
Yeah.
and this is what we call new particles
Yeah.
that you don't know yet.
Yeah.
And you also use algorithm
Yeah.
to ignore so many other particles.
Yeah.
Are you assuming that you know these other particles?
Yeah.
So you know all of them.
Yeah.
Everyone.
Right. So the question was, now we're talking about trying to find new particles, and we've heard over the last lectures that we use algorithms to decide what data to throw away, and then we use algorithms to analyze the data that we keep. And in order to find something new, don't you have to know everything else that's out there, or else is it even new? And exactly that is 100% true. And so in a few slides, I'll show you how we do simulations of these new models of physics using exactly the same techniques as last lecture. And there's a baked-in assumption that we understand everything else, which clearly is not 100% true. And there's ways that you caveat it, and a lot of it comes into the uncertainties. But yeah, it's true. Yeah.
So you had to sort of propose new physics that,
Yeah.
if you follow the thread, sort of addresses these two
Yeah.
big puzzles. Where was the sort of intuition for the new physics coming from? Is it like following some mathematical thread, or?
Right. So let me say, so the question was, we have these two big problems that have been known in physics for a long time. And then I told you that what we're looking for is exactly this type of particle production. And what's kind of the intuition for how you get to something like this. And if there's a prescription, like a mathematical prescription for getting there. I think my high level answer is there's a prescription for doing the calculations, but then from the people who came up with this, there's kind of moments of brilliance of realizing that having particles of this property could solve a big problem like this. So for example, this type of particle, the idea here was that for every spin 1/2 particle, you would have a partner that was a spin 1, and vice versa. And so this was an idea, like you said, called supersymmetry from the 70s. And so this whole formulation then got produced and yielded predictions like this. Now, this one, needing something that violates the matter-antimatter symmetry, this was actually a set of conditions by, I think, a Russian physicist in the 80s that laid out 3 conditions to actually generate a matter-antimatter symmetry, and they used that intuition to arrive at particles like this. Yeah. Yeah.
I also noticed that the two puzzles are
Yeah.
enumerated 1 and 5.
Yeah.
Is there a sort of
Yeah.
famous list of
Yeah. Yeah, I think if I remember, I don't know if you were at the second one. So in the second lecture, what we did is we went through big problems in physics, and we basically, there's a giant list of them. But to me, there's really like 7 really big problems that are kind of looming over everything else. And in that 7, these were the 1 and 5. Yeah. Yeah.
And those probabilities on the charts you had, the probabilities, those are based on a specific set of particles coming in,
Yep.
proton collision, and a specific energy. So
Yeah.
there might be other ones that increase the odds.
Yeah. Lots of knobs to tune. Yeah. Yeah. No. Okay. Okay.
I was thinking, you're looking for new particles.
Yeah.
And I was thinking, could AI, through my program, we have put in reasonableness checks, could it reasonably be true that it is what you think it is, or you found what you found? But with quantum mechanics, it's not always reasonable, so can you even use AI?
Right. Right.
To check reasonableness?
Right. So the question was, can we use AI to check, say we find something that we think is new, can we use AI to give us a confirmation that it is new? Right now, with the state-of-the-art that we have, no. We're starting to use AI to do the statistical tests, which tell us if we see a little bump, how significant is that bump? And it's early days of using AI to do those type of tests, but really not yet. Yeah. 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 Okay, and then I got to be careful on. Yeah.
I'm trying to understand the matter-antimatter puzzle in the sense, is your solution saying that no matter what configuration you start with, these interactions are such that will end up with antisymmetry? I mean, does the
Yeah.
initial configuration matter at all?
Yeah. So the question was, it was about matter-antimatter asymmetry, right? That we've heard that we've observed a matter-antimatter asymmetry, and then I tell you that we have a new type of process that could generate it, but do the initial conditions matter? Do all the details in between matter? From all of the details do matter, but from our perspective as an experimentalist, all that we know is the final experimental measurement, which is that we observe an asymmetry. And so when we're testing models in new physics, we test things that could yield that new asymmetry, regardless of all the initial details, all of these things, but we factor that in. So like when we're doing calculations of could this lead to an asymmetry, if the initial conditions were way different, then it wouldn't. And then we don't test those things as much. Yeah, okay. 2 more questions. Yeah.
The purpose of discovering high mass particle is to explain gravity?
No. Sorry. The question was the purpose of looking for new high mass particles is to explain gravity. No. What we're talking about here is we have 2 different theories right now that at some point probably need to meet. There's general relativity, which gives us gravity, and then there's the standard model, which is the theory of the small, so quantum mechanics basically. And the gap between them is a very large energy gap, where gravity, the energy scale of gravity, is something like 10 to the 19 times more energetic than the weak scale when you talk about length scales. And so what this new particle is trying to do is not solve gravity, but make a bridge between them so that there's now not this massive gap. And so you put a particle that's sitting right in between, and it serves as a bridge between these 2. Let me go there and then, yeah.
Your graph shows probability of finding certain particles whose the reaction with collapse, so to speak.
Exactly.
Is a desire to find out what the probability of such reactions happen in the development of a universe. Is that the ultimate goal for this type of work?
Right. So the question was a very big question, which is we're looking at probabilities here, and is the ultimate goal of this to effectively have a table of all of the probabilities for all possible interactions which could have happened in the early universe? That's roughly a good way to say it. Maybe a different way to say it is we would like to have a theory that predicts all of the probabilities when we calculate it from the theory. And so remember that cup picture I showed where you had an equation on it, the standard model equation? That equation predicts all of these probabilities. And so what we would like is an equation that predicts them all, that we then go check with experiment and matches exactly. And then we can go and ask questions about the early universe and see if it actually gives us features like the matter-antimatter asymmetry. Yeah. And then, yeah.
So I'm confused about your use of the word scale.
Okay.
So you talked about energies and so on. So is it fair to say that you're measuring forces? I mean, one way to consider scales, let me think about the force of 2 particles, for example, at a fixed distance apart for a fixed force.
Mm-hmm.
And then what is the gravitational component of that? What is the weak force interaction?
Yeah.
Is that what you mean by
Yeah.
scale?
Yeah. So the question was, I'm talking about scale in different ways here, length scales, energy scales, and what do we really mean? And so what he was saying was that what we really mean here is if we took 2 particles next to each other, the force between them, how strong is that force as a function of distance? And so for the weak interaction, we have one set of strengths, and for the gravitational interaction, we have a different set of strengths. And the gap between them, how strong the forces are, changes like 10 to the 19, the gap
So you
between.
have to hold the distance constant
Yes.
to make that comparison.
Yeah.
Right.
And then you can also ask, how does the force change over distance? Yeah, and that's, yeah, exactly. Okay, very last question. Yeah.
Is there any possibility of like the timing between a LIGO detection and a gravitational wave producing a particle that would, of course, be within the detector?
Yeah. Right. So the question was, is there any chance that a gravitational wave that LIGO might produce, the LIGO might detect, could produce a new particle in here that we could see? I'm sure you could cook up some calculation that some small probability of it, but not that I know of. Yeah. Yeah. Okay. So where we left off was that to actually think about trying to measure and search for these particles, you need hundreds of billions of collisions. And to get to the rarest probabilities, you need millions of billions. And so then the next part of that paper, how it would go, is it would tell you what data are we looking at. And so we're looking at data from the second run of the LHC. And so this is the plot that I showed you in lecture 1, where along the x-axis, it's the year. So starting in 2010 all the way up to 2045 when the LHC will end. Along the y-axis are, this one I'll focus here, billions of collisions, and then gigabytes of data produced. And we're talking about data from this period here, where it's roughly 14 million billion collisions, resulting in something like hundreds of petabytes of data. And for reference, the line that we put last time is this here is the total amount of data on the internet. And so we're talking about this much, which you see here is 1/10 of all of the data on the internet. So we're really, really talking about a lot. And then in all of that data, millions of billions of collisions, you have to actually find your signal. So this needle in a haystack idea. And so what we're looking for is particles that are produced and then result in jets like this. So this is an event display from the detector where you see collimated sprays of energy. So these energy are deposits in the calorimeters from quarks being produced, and as they go through and hadronize, they deposit energy. Now, a problem with this type of signature is it looks identical to what happens in the standard model already. If you just shoot in 2 protons, you can get things that look like this most often, all the time. And so you have to actually disentangle them by analyzing really complex data. And to make it more clear, in essence what we're doing is we look at millions of billions of pictures like this, and you look at this, you see a spray of particles here, 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 all over, and you ask, was there a new particle produced inside of here? And so you look at this and you say, I don't know, maybe. And then you look at this and you say, I don't know, maybe. And then you look at this one and you say, no, there's for sure not. This is not what we're looking for. And how you could know that is in this nice event display. Well, one, you only see 2 really pronounced jets of particles, which are these. And then also, this dashed line means that there is a lot of missing energy. So you could have had neutrinos produced or other things that didn't interact with the detector at all and just escaped. And that's not what we're looking for in this particular analysis. What we're looking for is all of the energy being measured, nothing escaping, and you really seeing tons and tons of jets. And so you can put together kind of an algorithm like that, but something that I hope is clear in all of this is that we really rely on having an expectation for what the physics should look like. I mean, I'm talking about you expecting to see jets, you're expecting to see no missing energy. You needed to know what this would even do in the first place. And that was the entire discussion from last time, actually doing simulations. And so this is an actual Feynman diagram from the process that we're interested in, where you have 2 protons coming in, you produce 2 heavy particles, they decay through some coupling, and then you get quarks in the final state. And just like in lecture 6 where we talked about actually calculating all of these different Feynman diagrams, those exact same methods we used here to get simulations, which then were used to make decisions of this looks like our physics, this doesn't look like our physics. And to say that in a different way, once you have those simulations, you can get expectations for how many sprays of particles you expect to see. And so what you're looking at here is along this axis, it's the number of jets, where each jet is a spray like this. And along the y-axis is the fraction of events that has that many jets. And so this, you see, these are all the signals. These are the hypothetical particles, where you see they peak at roughly 6. So you have, on average, 6 sprays of particles like this, whereas the background, everything else in the standard model, is peaking at like 3 or 4. And so you have this idea of what you think should happen. You do all these collisions, and then just like we talked about, you actually need to save it. And so we build a trigger just based on this information. So we have a trigger that all that it does is it calculates how many jets we saw, adds up their energies, and makes a decision in 2.5 nanoseconds, 2.5 microseconds to save an event. So to say that again, what goes into a plot like this is we do simulations of exactly a diagram like this. Out of it, we get a prediction for how many sprays of particles will be produced. We take that prediction, we put it into an algorithm that says just sum up the energies. We run that in the experiment, decisions every 2.5 microseconds, and then we save a bunch of data. And after doing that, we end up with something like 10,000 to 10 million times more background than signal. So what you're looking at here is some kind of arbitrary axis that tells you about the momentum of the jets, and then the number of events. And really what I want you to look at is this line here, which is the background, and these lines here, which are the signal. And this is already a 1/10 reduction of the background. And you have a gap here of 10 to the 6th compared to 10 to the 2. So you have at least 10,000 more background here. And in other plots I could show you, you have 10 million more times background. And so it just emphasizes again, you're taking all your data, you've designed a trigger that you think is supposed to pick up just your signal. And when you take all of the data, you then end up in a scenario where you have 10 million more background events for every single one of your real event. And somehow you need to navigate through this to actually find what you're interested in. And so then you need to actually identify the needle in the haystack and use the unique properties of this. And the unique properties of this, the one that in particular we're interested in, is one that you've seen a lot. There's a resonance here. This new particle is supposed to be massive, which means that what you should see is a similar type of signature that you've seen all over. There was the one that I showed you from the intro, where this is the production of this J psi particle that was 50 years ago. You see this clear peak. You have the top quark that was discovered just down the road at Fermilab, where again you have this clear peak. You have the Higgs boson at CERN, where you have this falling background and then a peak on it. And so these resonances, what they're really saying is right at this mass, you have an increased probability of making a particle like this. And so every time we say particles, in translation, we mean a resonance like this. And so really what we need to do is we need to infer the properties of this particle by studying all of this data, which is exactly what we did in Lecture 4. So in Lecture 4, if we remember, everything that we talked about was we produce a top quark, a B quark, and a W boson. We get hits in the detector. We analyze those hits using AI, and then we go back to the properties of the top quark. Now what we're doing is we analyze all of these hits here using an AI algorithm, and we guess the mass of the new particle. And so what you're looking at here is after running an AI algorithm on a bunch of different collisions, the predicted masses. And so this is one where in simulation, I predict the mass to be 1,000 times that of the proton, and then this solid line here is what the AI predicts. And the point is that they're on top of each other. And so we're using these techniques to actually predict the masses, whereas in the case of the top quark and the bottom quark, what we were doing is looking at a jet like this and just trying to guess, is it a bottom quark? Now we're trying to guess a next level thing, which is not only is it a new particle, but what is its mass? And if you looked under the hood of this, you would actually see basically all of the new techniques that are being used across the industry. So if you go and look at the code, you'll see basic core ideas from neural nets that are used in, for example, AlphaFold, which is what just won the Nobel Prize in, I think it was in chemistry. So the basic building blocks of our model is the same as used in here. And then also it's what is powering ChatGPT, but on a much larger scale. And so the same type of techniques are being used. And there's been a lot of questions about what type of hardware we use. And to do this entire thing, we use the single GPU that actually we bought at Best Buy. So we really can use things that are right off the shelf running newest algorithms. And so then what we go and look for is exactly like in the Higgs case, a background that is falling off, and then we look for a resonance. And now this resonance is much rarer and much broader, and so we scan this background, and then we look for, are there any bumps? And something that you can see is at this tail end, you start to see deviations, but this tail end are the most energetic, and this is just that we're running out of data. There's no new physics here. This is simply that to get things like this, instead of hundreds of billions of collisions, you actually need billions of collisions. And so you can already see roughly where our sensitivity is maxing out, around this point here. And so then we can go and set limits, because we haven't found anything new, exactly like we talked about in Lecture 3. Now remember in Lecture 3 we talked about there was the collider at Fermilab, there was the collider at CERN, and before the LHC even turned on, we could set limits on what the possible mass of the Higgs boson was. And we saw plots like this where we had this green band, and the Higgs mass could be inside of here. Now what we're doing is instead of the Higgs mass here, it's the new particle mass here. This is the theory prediction, and everything over here we've now ruled out. And this sets the stage for next set of experiments. We'll come and look in this range here. And so then you look at this, and at this point you will be at the end of the paper, and then you'll sit and ask yourself, okay, what the hell did I just do? What did I just learn? And so you ponder, is what this is telling us that this thing is just fictitious, that it's not real at all, that it is not actually in nature, and we will never find a particle like this? It could tell you that. It could tell you that all of your algorithm and your trigger and everything that you designed just missed it. So it could be that the algorithms running were not good enough. It could be that you didn't do enough data. It could be any of that. It could also be that in doing the simulation, you thought you understood stuff, but you didn't really understand stuff, and so you just missed it. And so you look at these, and you can really then ask the question of what is ruled out. And so I'll pause a second to just ask if there's any question on this, because then I'm going to make one more point with it. Yeah?
How confident are you that we'll actually find something?
Right. The question is, how confident are you that we'll actually find something? I think if you had asked people 15 years ago, the answer would have been very confident. If you ask me now, I'm not that confident. I'm not really sure. I would say I'm roughly 50-50. Yeah. And part of why I'm roughly 50-50 is as we get to these higher and higher energy scales, the original motivation behind doing searches like this start to get weaker and weaker. And so the theory motivation starts to drop off more and more, and you're really entering new territory where you don't necessarily have a good grounding. Yeah.
You said earlier you predicted the mass, and then the AI model also confirmed that. Question is, was that prediction based on theory or based on what you have seen in the data?
Right. So the question was here, I said that we predicted the mass, and then the AI confirmed it. So I think I maybe misspoke a little bit. What I meant was this line up here is entirely theory calculation. So the theory calculates it, and then you run simulations like what we talked about last time. And then with those simulations, you get images of what could happen in the detector, and then you have an AI look at those images and then predict the mass. So do the inverse problem, which is to emphasize this is a problem of looking at measurements on a meter scale and making predictions on the 10 to the minus 18 meter scale. And that's what this is. And so what you take away from this plot is that from all of the theory calculations, you get a mass peak like this, and then the AI gives you basically spot on. Yeah. Yeah. But sorry, this is all hypothetical particle. These don't exist. And in fact, we know that they don't exist at least up until this mass point, and that was the whole point. Yeah.
It's a follow-up.
Yeah.
My question earlier
Yeah.
about two protons producing Higgs. What happens to E equals mc squared? I mean,
Mhm.
you got this huge mass, okay, and you didn't put the energy just from two protons to produce. So this m E equals mc squared is up the window.
So the question was, from E equals mc squared, you shot in two protons, which were 1/125th the mass of the Higgs, and then you produced the Higgs. So is E equals mc squared just wrong? Well, you're missing a term. You're missing the p squared. You're missing the momentum terms.
Yeah, but still, if you take the momentum into account,
Yeah.
still it doesn't come up to that value. It's a huge
Yeah.
discrepancy. The momentum is not that big.
Right, but this is exactly why we're colliding at such high energies. The energies that we're colliding at, 13.6 TeV, this is 130 times the mass of the Higgs. We're shooting these things in at momentums much, much, much greater than the mass of the Higgs. And so they really do have this much energy. The momentum is massive. Massive, massive, massive. Yeah. Afterwards, we can do the math on the board, and I'll...
One more question.
Yeah.
Every protons that you accelerate into colliding beams, every proton collides, or there are some that do not.
No.
And so there are some that don't.
Yeah, so the question was, when we shoot in these protons, does every single one collide, or there's some that don't? So what we do is we shoot in bunches of protons. So like bunches, each bunch is like 10 to the 12th protons. And per bunch crossing, we have like 60 collisions. 60 versus 10 to the 12th or something. So very, very few collide. And just really appreciate that. When we're talking about 14 million billion collisions, that's 14 million billion collisions, but only 60 happen every time you cross 10 to the 12th of them. And so you're talking about even orders of magnitude more protons being shot in. Yeah. Behind, and then I'll come. Yeah.
So you ruled out, like, the thing you're looking for
Yeah.
doesn't exist if it had a mass below this point, right?
Yeah.
But does it kind of make it more, like, maybe less likely but more exciting if you find it because of that ladder description you had, where it's like closer to the middle of
Yeah.
what it would be?
Yeah, so the question was, okay, we've ruled it up to this point, and then does it make it more exciting if it would pop up at a different mass? And the answer is absolutely. Each day that we don't find something, the tension grows if we're going to find something at a higher mass. But then you can ask the reverse question, which is, are you still motivated to go look for it? And then you start to get in more interesting questions of, would you even invest? I mean, this result here took 3 years. So would you really invest 3 years to go and look for something if your idea of it happening is smaller and smaller? I don't know. Yeah, yeah, yeah.
So, if I'm interpreting this correctly, the graviton, if it exists, is way down past the bottom of this chart here. It should be a massive, mass in order to discover it. But the reason why gravity works at such large distances is because in that huge amount of space, there's a lot of energy, and therefore there are a lot of gravitons bouncing around. Does that seem to be?
Right, so the question was, if we're talking about gravitons and it exists over here, the scale difference between gravity and these gravitons, the important thing here, I think the G that I was using for the new particle was confusing. We're not talking about gravitons.
Oh, I know.
Yeah.
Theoretically.
If a graviton existed, you're saying. Well, if a graviton existed, it would have to explain, I don't want to go all the way back to it would have to dynamically generate that scale. And really, again, what we're talking about is just a bridge between. Did that answer your question or not at all?
It's getting there.
Okay, afterwards come in and, yeah.
If I'm thinking in a Newton way,
Yeah.
when the protons hit, they don't always hit at they go off at various angles. Is that taken into account?
Yep. Yep. The question was when the protons hit, they can be elastic scattering, inelastic scattering. They could just glance off each other and go off. And is that taken into account? Yeah. Absolutely taken into account. And things that I haven't shown you, for example, is I showed you where the experiment is, and I showed you the detectors. Actually, we have additional detectors hundreds of meters downstream that measure protons that come in, don't hit, and just glance off each other, and then actually make it all the way out. And all of that's factored into these calculations. Yeah. Yeah.
I have a question about like the particle itself.
Okay.
Is this like the first step, at least, in merging quantum mechanics and general relativity? Is that the idea?
Yeah, so the question was, is this the first step in merging general relativity and quantum mechanics? For this type of search that we're talking about here, the answer is no. What we're talking about here is really just making a bridge between them in energy scale, but we're not modifying either theory. Meaning, to really get a merger of them, you need some theory that's really sitting above that links them to. And all that we're talking about is expanding the standard model. We're just expanding our current theory. So when you talk about merging the two of them, you really need something even more above this. Now, basic ingredient like this could give you something like that, but I think it would be not fair to say this is really.
I guess the term bridge sort of
Okay. Okay. Afterwards, come and talk, and I can show you some more plots and stuff. Okay, it's almost noon, and I have maybe like 10 more slides that talk about like future direction. Do you want me to go through them, or? Okay. 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 I actually wanted to make one more point about this. Was that you see this is all ruled out, but there's a bunch of different colors, and the colors that I actually wanted to highlight was there's this blue line here, so there's this big blue line, and then there's this dashed blue line. Do people see this dashed blue line? People see what I'm talking? Okay. And then there's a red dashed line. And so what we actually did was we compared a non-AI-based method to the AI-based method and asked how much better is one versus the other. Is it even better? And what we found is that for the non-AI-based method to be as powerful as the AI-based one, you would need around 9 times more data. So you are more efficiently using your data, 9 times more data. This is instead of 14 million billion, you need 140 million billion collisions to reach the same level of power as the AI algorithm. And so this is really saying all that hard work, okay, maybe you're sad that you didn't find anything, but if now you're thinking, well, we're going to now get a 20x increase in data, this method and methods like this will for sure be used. You're going to get even more sensitive in the future. The algorithms will get even better, and then maybe instead of 9x improvements, you'll see 10x improvements. You'll see 15x improvements. Other analyses now are even seeing as much as 20x improvements. So it's really a big improvement. And so I'm glad that we're getting so many questions. And to emphasize, the whole reason that we're talking about this is I just wanted to make the point that with everything that you've seen so far, you're really looking at a brand new analysis. Like a brand new one. I mean, this is posted. I have a timestamp here. This is October 10th, 2024. So like really, really fresh out of the collaborations. And so you can basically understand most of everything that's posted on our websites now if you wanted to go and look for stuff. But so in the next 10 minutes, the last 10 slides I want to do was just show you how a lot of the ideas, when we now think about what to do next in the analyses, the core ideas serve as a grounding for those next ideas too. And so the first one is this idea of triggering. And so we were talking about looking at mass at this purple line, where they have this probability, but there's all these other lines, and the other lines matter also. And in particular, as you start to go to these other type of new physics scenarios, you go to lower masses and rarer probabilities. And what that means is that the number of jets and how energetic they are shifts left. And so in the detector, instead of seeing 6 jets of particles at really high energies, you may see 4 at less energies. And what that means is that our current triggers wouldn't take that data at all. It would be completely thrown away. And so now there's ideas for actually a new type, well, this is already being used, a new type of triggering protocol where what you do is you reduce the file size. Instead of 2 megabytes per event, you save 100 kilobytes per event. So you reduce the file size by like 60. In doing so, you throw away a lot of the data, and you only keep a tiny, tiny portion of it that you need to do this very specific type of physics. And when you do that, you can then ramp up how many events you save, because now you don't have this problem that 2 megabytes per second times billions of collisions takes all of your hard drive space. Now you're saving less data per event, and you save more of it. And so this is actually already being deployed. And this is a plot from the competing experiment, where this is the plot that I showed you, and along the x-axis, you see it's peaking. It's going all the way to like 3,000 giga-electron volts. And now they're probing masses that are 10 times lower. And so that's to say that on this, instead of being on this purple line, they're probing on this blue line. And that's only possible by putting new algorithms inside of the trigger, because if they didn't do that, all of the data in this plot wouldn't have been saved. And so this core idea of doing data compression on the detector, or really close to the detector, and saving less amounts of data per event, this is going to be a giant pillar that you'll see tons of analyses for maybe the next 5 years, 8 years. And you'll see tons of things coming out of CERN using ideas like this. And it's really early days, because all of these compression is just based on classical computing. And once AI starts doing the compression for us, things will get even better. And then the second thing is an idea that we talked about before, which was that everything that we've talked about so far is for a very specific model. So it was this specific type of particle going to 3 quarks each. But you could imagine making an AI that does it much more generally. So instead of looking for this type of, this case is called a gluino, you look for a generic particle, and that particle generically decays into some number of quarks. So a much more abstract idea, where in doing this, you basically throw away all of the theory calculations, and you say, if we haven't found new physics yet, probably theory is walking down the wrong path, but we have the experiment, and we can actually just go look at the data. But to do that, we need to tune the algorithms to be more general and not rely on the theory calculations. And only now, recently, in maybe the past 8 months, 9 months, can you envision making an algorithm that uses AI to actually do this. And so what you're seeing here is the same mass along the x-axis, but now instead of a specific model, it's a general model. So this is any type of particle x, going to any number of quarks on either side, and you still get almost perfect mass reconstruction. And so what will happen here is that now the collaborations are taking these algorithms that don't rely on theory predictions and going and running them at the triggering step to save data that wasn't previously saved. They're running it at the analysis step to get more sensitivity to new types of physics, and they're really running it everywhere. And so, again, the overarching point of all of this was just that from everything that you've learned, you'll now see all of the new experiments turn online. So like the high luminosity LHC in the next maybe 5 years or so, ramping up of the computing capacity from 450,000 CPUs to maybe millions or millions and millions all over. You'll see new detectors installed, new types of microelectronics installed, but all of the core ideas from the past lectures that you guys have listened to and understood will be the grounding for everything you'll see. And so you could really go look at a lot of the briefings and understand mostly everything. And so next time, in the last lecture, now we're going to use this and talk about more of these future directions. So maybe a future experiment, maybe future microelectronics like chip development. I'll see kind of if there's more questions to tune it in a certain direction. But that's all I wanted to talk about today. So thanks a lot for all the questions. And yeah.
That accelerated proton has a kinetic energy. That's mv squared. And let's say the velocity is the speed of light. Still, this would be half of its energy related to mass as E equals mc squared. So in this case, the total energy cannot be more than 1.5 mc squared.
Mhm.
And two of them, they will have the double, so that's 3 times. How do we get 125? So this is one part of the equation. The other part is we are losing, we are reducing this Higgs particle, and then it decays. When it decays, in this case, its mass should also follow E equal mc squared, which that means it should produce 125 times the energy of one proton. Okay? So that means we start with the 3 mc squares, and then we get 125 mc squares. Okay, is that like we are getting energy for free or something?
Anthony, would you do a favor? Write on the equation the expression for the total energy of a particle, including its rest energy and its
Yeah, so you have E equals mc squared plus p squared c to the fourth.
So what does each of those terms mean?
So everything that you're talking about has been the rest mass of the particles. So that's this mc squared term. But the full energy momentum conservation includes a momentum term with the whole thing is conserved. And so this is the momentum of the particles. And this total term is what's conserved.
But P,
Yeah.
P is really comes from the kinetic energy. The momentum.
Mm-hmm.
Because any particle moving has an energy half mv squared, and its momentum is mv. Okay?
In classical mechanics, half mv squared.
So in this case, this will be true only if the relativity is true. What you wrote on the
If I understood you, this equation relies on relativity. If what we're talking, maybe I'm missing it. If what we're talking about is relativity wrong, that's a different question. That's I'm not thinking.
This is true only if relativity is true. You are assuming that relativity is absolute given true. Yes.
Yes. Yeah.
But this formula that Anthony kindly wrote down, the P there is not MV.
Yeah.
That's a big mistake. P is the different expression of relativity. And when the velocity goes to 0, that second term goes to 0.
So how do we calculate P?
Okay. Yeah, I can show you. I can show you more later. Implicitly in all of this is a belief that all of the experiments that we've done in the past testing special relativity have put it on good footing, and we trust it. And at least for me, we trust it because all the satellites don't fall on our heads, and we do all the calculations with that, and plenty of experiments have tested these ideas. But the real root of your question of going from the lower mass states to the higher mass states, it relies on things like this. I've avoided saying words like off-shell, which is that you can produce a particle. When I talk about a Higgs particle at 125 GeV, what we mean when we say that is Where does 125 come from? Maybe I went too far. It just comes from that's when you get an increase in the probability to make the particle. But you could get Higgs produced at lower masses. That's just not usually what we talk about. But I've avoided this because I don't think that's what you're talking about. I think you're talking more about this.
Is there
Yeah.
any attempt to increase the lifetime of Higgs particles so it stays there for a while?
Sure.
Study it more.
Sure. I thought you were going one way, and then you ended going a different way. I thought you were going a way that was, has there been attempts to calculate what a longer lifetime Higgs would look like in the detector and test how long it's lived? Like, question the idea that we know its lifetime. That has for sure been done, and we've ruled out basically every other scenario for how long it lives. And what we're at is that it lives something like 10 to the minus 23 seconds. But we've tested plenty of other hypotheses. And those were tested at Fermilab, those were tested at CERN. If the other thing that you're talking about is, can we create an experiment where we induce the Higgs to live longer? This is a different set of questions. And if you somehow got the Higgs at infinite velocity, or infinite momentum, so it was so you had time dilation, so it was super long-lived. But even then, you're not talking about, it's not going to be interacting with the detector. And then I don't really know how to do that. Experimentally, I don't know how to do this. Yeah.
Yeah, so you find the particle that's way out in that particle mass desert.
Yeah.
It's suspected that it would be the smallest mass supersymmetric particle. And do we have any way of guessing what that would be? And can you tell any other properties? I mean, all you're getting really by is the mass. So
Yeah.
you really know that that's what it is, a score.
Yeah. So the question was, in here, I can even do it in, in here, I've been talking about this one particle here, which is this G tilde. And the question was about the theory that this is based on. And the theory that this is based on is called supersymmetry. And the idea is that every particle in the standard model, you have a copy of it at a different spin. And so this particle is the copy of the gluon. This one here is the copy of the gluon.
You always get these two jets.
Yeah, yeah.
And that's the symmetry.
Yeah. And so then the question was, doing these measurements, I think the question was, doing measurements like this, all of the other particles that the model predicts, do you understand better where they should be too?
Right. What was the mass spectrum?
Yeah.
Any way to get that in theory?
Yeah.
All you're going to find is the lowest mass.
Yeah. Yeah. So from theory, we can make predictions of exactly the mass spectrum, but we make predictions of many possible options of the mass spectrum, and we don't know which one is the right one. And when everything coming out of the data that you've heard of, we've ruled out supersymmetry, is that we've ruled out the simplest mass spectrums. So ones where the partner of the top quark would be the lowest mass, and then the gluino partner of the gluon would be the next one. So we're able to rule out different mass orderings, but we don't know which one is right. We don't know, even if, these particles could not exist. The whole thing could be false.
Quick follow-up.
Yeah.
Is there a supersymmetric particle that matches the Higgs?
Yes, but maybe a more involved question than you may think it is. The Higgs, there is a partner to it, but like, for example, the W boson, the Z boson, and the photon, those are made from other types of particles when the symmetry breaking happens. So I don't want to say too much, because this is a more involved theory question where there is a match, but not exactly in something that I can do without writing on the board. Yeah. There's mixings that can happen.
It's its own.
Yeah. Yeah. There's a, yeah. But you can have multiple of them, is why I hold it on that. Is you can have not just one pair, but multiple versions of the Higgs. And so, yeah. There's no end to it. But to emphasize, all of these things The whole point is those two questions we laid out at the beginning, we're trying to answer those questions. And so from an experimental side, we have a set of physics questions, and we're trying to test ideas to solve them. And if supersymmetry can solve it, great. But if we rule it out, there will be other explanations because we don't know what the answer is. Yeah?
Can we go back to a basic structure of neutron and proton?
Okay.
Just 3 quarks, right? Up and down.
Mm-hmm.
Each quark has about a mass of what, 5 MeVs? Up down.
Something like that. 2 MeV, yeah.
The proton has 1,000 MeVs.
Yeah.
So where does it? A total quark is only 15 MeVs.
Yeah.
And the proton is 1,000 MeVs.
Yeah.
What else is in the quarks?
All of the gluons that are keeping the proton together, all of the gluons gluing it together is exactly making up that. Yeah. 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 Any other questions?
You talked about moving from heavier interactions to lighter interactions instead of 2 MB.
Yeah.
100. So earlier you talked a lot about triggering,
Yeah.
keeping only a few of the particles.
Yeah.
But isn't there a trade-off between keeping more interactions versus less data? When you do decide to keep data about an interaction,
Yeah.
what do you keep? Do you compress it very well?
Yeah. Yeah. So the question was, when we talk about new triggering ideas to go to lighter mass particles, go one step back and ask, what do we keep per collision anyways, and what are we now not keeping? And so typically for maybe this one I can show you with the event display, it'll be better. Yeah. So typically, remember that there's this whole detector around it, this big thing. Usually, for every event, we save roughly every electrical channel data. Every single one. We do some filtering, but basically every single one. And the sum of that is around 2 megabytes. Now when we talk about reducing that, literally what we're doing is, for example, don't save anything from the silicon inner detector. Compute things with it in real time, make some decisions, and then don't save it at all, but save everything else. And in doing trade-offs like that, you can reduce from 2 megabytes down to 1 megabyte, down to 500 kilobytes, just by picking which pieces of the detector you save. And then you can imagine this is some game of what pieces of the detector do I need to do my analysis at the end. And so then you get different schemes like that. But all of those right now is us by hand effectively going in and saying, save this, don't save this, don't save this. Whereas you could imagine schemes in the future of a computer automatically compressing, doing some form of compression, and returning for us summaries of the events. Hasn't really happened yet. Yeah, but the ideas are there. Yeah. Yeah.
What are the major centers where this research is being done? I'm saying around the U.S. Is a lot being done here at UC?
Right, so the question, what is the major centers? I guess there's 2 versions. There's where are researchers thinking about this, and that's basically every university, every big research university. Where's the actual facilities? This one is entirely in Switzerland. There's a big one, not like this, but for a different type of physics, being built at Fermilab, so like an hour away. There's another one in Brookhaven, so along Long Island. And then there's one kind of near Stanford. And those are really the big facilities. But people think about stuff like this and do analyze the data at most of the universities. Yeah.
Are the Russians or Chinese?
Yeah, they have their own. I mean, next time I'll probably mention the talks of the next version of this, and which are happening right now. And the Chinese, for example, have a proposal to build an entire collider on Chinese soil that will be much more powerful than the LHC. The Russians, at one point in time, had things like this. They now don't have, for the most part, don't have facilities of this scale. They focus on less energetic collisions, more for nuclear physics type research. And other places, Japan is super big in this. They're also talking about building the next version of CERN on Japanese soil. So I think I think in my first lecture I had in a backup a map of the world with the different labs, and maybe 4 out of the major ones are in the US. Then there's CERN, then there's 1 in Italy, 1 in France, 2 in Japan, 1 in Russia, and then 2 to 3 in China. So international in the sense that a lot of different countries working on it, not so international in the sense the labs are really in 4 countries. And
Do we get the results of their research pretty freely in the
yeah.
scientific community?
Yeah, so the question is, do we get the results of their research pretty freely? So far that I can see, yes. I've never doubted any result coming out of anywhere else. I mean, in particular, a lot of the things that we're talking about is really funny when you go look at the history. Like, a lot of things I've shown are like either a Nobel Prize given to an American or a Nobel Prize given to somebody. But you can go and look at like the Soviet times where they were doing a lot of the same calculations, and they have papers that were almost identical. And so they put out a lot of the results. There's now more of a discussion of if the next big collider gets built in a country that the US won't go work on, what happens? Like if everything gets built in China or something, will the US send researchers to go work there? That's above my pay grade. I don't know. But so far, I think everything is relatively trustworthy. Yeah, yeah. Yeah. Okay, well, if there's no other questions, I'll stick around for a little bit, but thanks a lot for coming.